Resistivity and resistance. How could the wire in the circuit affect the current? If wire is like a pipe and current is like water that flows through the pipe, what could we do to the pipes to change the amount of water that is moving through them? We could change the cross-sectional area of the pipe. Making it bigger would allow for more water to flow. We could also change the length of the pipe. Increasing the length will increase the time it takes for the water to get to the end of its trip. Every conductor conducts electric charge to a greater or lesser extent. The last example also applies to conductors like copper wire. Decreasing the length or increasing the cross-sectional area would increase conductivity. The inverse of conductivity is called resistivity. Each material has a different resistivity. Resistivity is abbreviated using the Greek letter rho, the curly P. Combining what we know about area, length, and resistivity, we can find a conductor's total resistance. Resistivity times length divided by area gives you resistance. So here's our equation for the resistance of a wire. We have resistance in R, measured in ohms. The cross-sectional area, A, is in square meters. Length, here, is in meters. And resistivity, rho, is measured in ohm meters. Materials with a low resistivity are preferred for making conducting wires and circuits. What is the resistivity of a good conductor? Low. Low resistivity means that electric charges are free to move in a conductor. Resistivities of common conductors. Here on the low end, we have silver and copper. Copper is what you're going to see the most in wires. Over here, at 100, we have nichrome, we have mercury. These are not good conductors as compared to copper. All copper wires have the same resistivity, no matter what size they are. So here we have two different wires, two different cross-sectional areas, two different lengths, but they're both made of copper. So both wires have a resistivity of 1.68 times 10 to the negative 8 ohm meters. However, these wires do have different resistances. Which wire has the least resistance? Answer on the next slide. Here, for resistance, we have rho L over A. All right, so that's our standard resistance. Here, our copper wire is 4 times as long, so we put a 4 in there. It also has twice the cross-sectional area, so 4 divided by 2 gives us 2 in front. So this wire has twice the resistance as this wire. So the shorter wire has half the resistance of the other wire, even though its cross-sectional area is smaller. What is the resistance of a 5-meter long tungsten wire with a cross-sectional area of 0.1 square millimeters? Okay, so we're going to use the resistance formula, but we cannot forget to convert these 0.1 square millimeters into square meters. So 0.1 square millimeters, we have a conversion factor here where 10 to the third millimeters is 1 meter, and we have to square it. So when we do this calculation, we get our cross-sectional area to be 0.1 times 10 to the negative 6 square meters. We plug the information in, and we get 2.8 ohms. An aluminum wire with a length of 9.43 times 10 to the second meters and a cross-sectional area of 10 square millimeters has a resistance of 2.5 ohms. What is the resistivity of the wire? All right, so first we're going to solve this equation for rho, for resistivity, and then plug in all of our numbers. Don't forget to convert 10 square millimeters to square meters, which is 10 times 10 to the negative 6 square meters. And we get this value here, which we can confirm by looking at our chart and looking up the aluminum. So all aluminum wires are going to have the same resistivity. What is the length of a 10 ohm copper wire with a radius of 1.6 millimeters? So first, let's solve this equation for L, because we're looking for length. So L equals RA over rho. And this is area. We are given a radius. So if this is our cross-sectional view of our pipe, we are given this value. So we're going to have to find the cross-sectional area using pi r squared. All right, so then here we convert our radius into meters. Then we plug in all of our numbers and we get 4.8 times 10 to the third meters.